Okay, Assalamualaikum warahmatullahi wabarakatuh. So this is our assignment for the subject Thermodynamics and Heat Transfer. Okay, so for this assignment, my group team members consists of 5 persons, which is the first one Muhammad Ashraf, the second one is Muhammad Naim, the third one is Muhammad Akmal, the fourth one is DANISH THAQIF, and the last one of these team members is myself, which is Muhammad FIKRI. Okay, so in this experiment, we are required to design and make a simple simulation and report on how we create heat sink by conduction graphical analysis on heat transfer. Okay, so basically what is heat sink? Okay, heat sink is a tool that we use to distribute and absorb heat that produced by mechanical or electrical system. Okay, so the heat sink will transport heat away from the heat generating components, so it will release the heat to the surrounding. Okay, so in order to maximize the heat dissipation, heat sink are often built of material with high thermal conductivity such as aluminium or copper. And for heat sink, in order to increase the heat dissipation, the high dissipation, we also need to make them in a wide surface area. Okay, so in many different field and business where thermal control is important, heat sinks are deployed. So such as in industry, in electronics, computer, automobile industry, aircraft industry, and aviation, communication, and many more industry that we use heat sink in these industries. Okay, so basically that is how and the importance of heat sink in industries and many application in this work.
So there is two type of design that we prepared for this. So the first one is a zigzag pattern. So on the left, there is dimension for the zigzag pattern. For the base, the height is 10 millimeters, and for the height of the zigzag pattern from the base is like 30 millimeters. So overall, it's like 40 millimeters, and the zigzag pattern exposed area is like 3 millimeters. And the second one is like a straight normal pattern. It's like a fries loop, and the base still same, which is 10 millimeters, and the height is also the same, 30 millimeters. So overall, it's same with the zigzag pattern, 40 millimeters. So we go on to the analysis. The first design, as you can see, the first picture, the temperature, you can see the gradient color shows the heat slowly turn into blue. You can see over there, the red slowly turn into blue, which means the high heat slowly decreasing into the low heat. You can see over here, it shows the maximum value is 390.600 Kelvin, and the minimum value is 390.232 Kelvin. So it shows the different value from bottom and top. So the first one is we're gonna show you guys the result, the tabulate result. As you can see here, the graph temperature against parametric distance. So the first one, it shows it increase linearly. So when we inverse the value, we get the second graph, which is inversely proportional. So onto the next picture, it shows the heat flux movement. You can see the arrow here, which indicates the heat movement, and the red one shows the high heat, and the blue one is the low heat. So it moves from the bottom of the sink slowly up and turns into blue, and that's why it shows the heat slowly decreasing, changing from high to low.
Hello, my name is Naim, and I'm going to talk about the second design. Based on the simulation result, we observe a minimum temperature of 3 to 1 Kelvin and a maximum temperature of 3 to 1 Kelvin on the fin surface. This temperature value indicate the thermal performance of the fin under the given conditions. Each plot is graphical representation that shows the temperature distribution along the edge of the fin. It provides insight into any potential temperature gradient or hotspot that may occur. By analyzing the each plot, we can identify areas that require further optimization to ensure uniform heat transfer. Next, we move to the next slide. According to the diagram, the heatsink bottom portion has the largest temperature distribution, and as you move away from it, the temperature decreases. The heat source then gradually moves to a different area of the heatsink. Conduction occurs because there is a contact area between the device and the heatsink in the current case. Conduction takes place when heat is transferred from the device and another electrical component to the heatsink. Convection then starts when the converting air intake removes the heat from the heatsink. Multi-phase fluid flow is present. Additionally, this explains why it is important to place or protect electronic components from heat source to avoid overheating and potential damage. Additionally, the relationship between the input wind and the heat sink maximum temperature is inverse. The maximum temperature of the heat sink decreases as the air entry velocity increases.
Next, I'm going to talk about discussion. For design 1 has favored more than design 2 since the thermal range for design 1 is lower than design 2, which is 319.232 Kelvin to 319.600 Kelvin, which is for design 2 more than 321.388 Kelvin to 321.619 Kelvin. For the next point, the number of fins represents the exposed surface area. More heat is removed when a larger surface area is exposed. As a result, the heat sink receives less heat. Next, the rate of heat transfer is higher if the fin is thinner. Lastly, the efficiency of a heat sink is determined by the fin spacing. The efficiency increases as the distance between fins decreases. Next, for comparison table. For the material, both of design using 1060 alloy. For number of fins, both of design use 10 of it. And at the same time, both of design have thickness of fin is 3 in mm and fin spacing in 1 mm. For design 1, the effectiveness is high, while the design 2, the effectiveness is low. The thermal range for design 1 is for maximum is 319.600, while the minimum is 319.232. Next, for the design 2, thermal range of it is for maximum 321.619, while the minimum is 321.388. For the shape, for design 1, the fin is zigzag, while the design 2 is straight.
So in conclusion, the 1060 alloy is a favorable material choice for heat sinks due to its excellent thermal conductivity, lightweight nature, corrosion resistance, cost effectiveness, machinability, compatibility with fabrication methods, and good electrical conductivity. The properties make it suitable for a wide range of heat sinks applications, particularly in electronics and thermal management systems. However, it is essential to evaluate the specific requirements of each application and consider alternative material if higher thermal conductivity or greater strength is needed. So that's all from us. Thank you.